Lab 6 magnetic molasses. So this lab investigated Faraday's law and Lenz's law, which is kind of a qualitative description of Faraday's law. Quick preview of results. I'll explain the experiment in a moment, but the computed drop time through the tube of our magnet should have been about 1.28 seconds, and in reality it averaged about 1.37 seconds. So some fundamental principles we need to do this experiment are, again, Faraday's law, which states that the induced EMF is equal to the number of rings, number of coils in a solenoid, times the change in magnetic flux over time. The magnetic flux is defined as the integral of the magnetic field, dotted with the change in area vector. We'll also need the law of gravitation down here, and primarily the Lorentz force as well, which states the net force on a moving object is given by the electric force plus the magnetic force. And now for this lab, the electric force will be 0. So we're really just looking at magnetic force portion. So here's what we did. We dropped a magnet down a hollow cardboard non-conducting tube that was wrapped in aluminum foil. And this would induce eddy currents as the magnet falls through the tube, which by Faraday's law, as we will explore, will result in a net upward force, or not a net upward force, but will contribute an upward force to the magnet as it falls, which will slow the falling of the magnet. So we see the velocity is pointed down, but we have some upward force that will slow it down. And we did this 5 times. The system is the magnet and the foil wrap tube, and the surrounding is everything else in the world. So here are some results. Namely, the magnet fell much slower through the tube than if we just dropped it like normally or through a non-foil wrap tube. And we also found that the magnet will fall the same way, the same amount of time, regardless of if the north or south pole is facing downward into the tube. So we did a computational model to confirm our results. This part of the code is measured in the lab. It tells us about the length and the width of the foil wrap tube. This equation creates a magnetic dipole and computes the magnetic field of that dipole. This part of the code computes the force vector generated from the magnet falling through the ring, falling through the tube. So we can envision just a bunch of rings of induced current as the magnet travels through the conductor wrapped tube. This will induce, by Faraday's law, this will induce the upward force that I talked about, and it will induce E non-Coulombic charges. So this code computes the magnitude of the force induced by the magnet moving through the tube. And again, this code continuously updates the magnet's velocity and position as it falls throughout the tube. Here are the results of this experiment, or of the computational model. This plot shows the velocity over time. So as the magnet enters the tube, it accelerates, at which point an equilibrium is established between the force of gravity pulling the magnet to the ground and the Lorentz force from the induced eddy currents pushing the magnet upward. So we have a constant velocity for a period of time, after which, as the magnet's beginning to exit the tube, the upward Lorentz force goes away, and so the magnet accelerates again as it falls out of the tube. And this predicts that the time it will take for the magnet to fall is about 1.28 seconds. So we only had about a 6.8% difference between the expected fall time for computational and experimental results. This is likely because it's hard to time with a timer down to less than 1/10 of a second. There's air resistance in real life, which we didn't account for computationally. It was hard to drop the magnet straight down, and it's possible that the foil was not wrapped in such a way as to make a uniform conductor. So what if the resistivity of the conductor were reduced as close to possible as 0? How would the dynamics of the magnet change? Well, since I equals V over R, if R goes to 0, I becomes humongous. And therefore, if the current becomes huge, then that means we have a large Lorentz force, which means that the magnet would fall very slowly, since the force pushing it upward would be stronger. And if R was actually 0, the magnet would levitate in the tube. And this is actually a kind of a oversimplification of how semiconductors or superconductors can elevate magnets. And if we cut holes or slots into the tube and into the foil, the circular induced currents would be messed up, and therefore the force pushing the magnet up would disappear, and the magnet would fall much faster, or as if the foil was not there, because there would be no upward Lorentz force.